some like Axios boulder that he's like the one-man band for. Yeah. So I think it's whenever anything happens in Twitter, we might wait like an extra minute or so.
Good answers, but I can try it.
We'll probably just wait an extra minute. Students just had student talks.
Yeah. They need a little pause. Yeah.
Okay, that's fine. And we can also see if there's like an NPC nearby, you can just.
Maybe whenever you're ready, we can get going.
Okay.
All right, well, let's get started for the next session. So we're happy to go back to Simon telling us about causality, unitarity, analyticity, and other things that end in ITY.
Yeah, except boundness. Boundinity. Okay, so I think so. Yeah. Welcome back, everyone. Yeah, so to summarize where we were last time. So last time we discussed Fourier transforms and Kramers-Kronig relation, and we said that the most causality and unitarity together imply that you have an analyticity in the upper half plane and some boundedness property that leads to dispersion relation of Kramers-Kronig type that we'll talk about more today. And one application we finished off last time with was the scattering phase in the theory where we had the so-called Gauss-Bonnet correction or aeroderivative corrections to Einstein gravity. And the eigenvalue of the scattering phase it was two different polarizations which had different eigenvalues, but causality required that this is positive, and therefore you learn essentially that the aeroderivative corrections can never dominate over GR in a regime where you have control. Okay, it's an important lesson. So aeroderivative correction always have to be small, otherwise we have to go to whatever is the UV theory that created this. One important lesson from this calculation is that this object here, as we discussed before, if you go to higher energies, eventually this phase will exponentiate. And then this phase has an interpretation in terms of a classical time delay. So if it exponentiates, then this phase is a time delay. Delta gives time delay, which is a very nice and pleasant interpretation, clear physical interpretation. However, if you try to actually use it in practice, you get bogged down into arguments as, does it actually exponentiate? And the important thing about this argument is that we did not need to exponentiate anything. The argument was valid in the Born regime, where we just have one graviton exchange, perturbation theory is in control. It's very controlled. This is not needed. Okay. So this is the sort of regimes we'll be talking about today. Regime where we're still at low energy, we don't have to resum anything. And we try to get a bit more quantitative version of this constraint, where we can actually say something about what are the heavy states which correspond to this new physics that appear at the scale. So the goal today is to, what is the space of effective theories? What is the space of effective theory that are consistent, that arise from, that admit causal UV completions? That is the main question to be discussed today. So for most of today, we will actually focus on a simple model without gravity. So it's going to be our simplest setup. So in terms of energy, we'll imagine we have some light scalar, and then nothing else up to some mass scale, capital M. And big M you should think of as a cutoff of your theory. And then could be anything here. We'll assume that physics is weakly coupled here in the low energies where we're going to assume a weakly coupled EFT. But in the UV above the scale M, we can assume anything. Things could interact strongly with each other. Could be anything happening here. We'll be agnostic about that. Okay. But we'll assume that at weak coupling, we have weak coupling. In order to have, that at low energies, we have weak coupling, in order to just parameterize the EFT in terms of Lagrangian and higher derivative corrections. And the philosophy here is we'll start by studying this theory at 3 level, and then try to see if what we do is stable against loops, and take a perturbative mindset. So simplest setup, we're going to do it for a single scalar field. And of course we assume that the mass of the scalar field is much less than capital M. The nice thing about the setup is that we can essentially almost completely solve it. So we can really understand what happened, and that will give you a flavor of the techniques we can use in this to answer this question, and a flavor of the results that come out. Then, so maybe I can give an example of a weakly coupled DFTs. So that are not of the single scalar type, but there's actually a lot of interesting weakly coupled DFTs that one can study in nature. So example here would be pions and large NQCD. That would be one example that people are studying using similar techniques. And because of large n, the interaction to the pions are suppressed by 1/n. The pions are still like strongly interacting bound states of quarks and gluons, but the interactions between the pions are small in this large n regime. Another example is gravity at energies much less than m Planck. So if you have any kind of weakly coupled UV completion of gravity, like string theory, you would be in this regime. Where, so those are some examples you can have in mind of this, about this paradigm. So I'm going to set up the problem and tell you about, so we want to constrain the EFTs. We should explain what the parameters are that we're trying to constrain. We have some kind of numerical bounds on them. So there are 2 ways to, say, parameterize EFTs. So one approach is just to give you what the action would be. Okay, so at low energies, we'll have an action that would be some integral, ddx. Now I'm going to write everything modulo factors as 2. We'll have some kinetic term, some mass term. maybe some cubic term, maybe some self-interaction, and then you will start adding higher derivative corrections to this. And for a reason that I'll explain in a minute, the first thing you can actually write down that actually does something is something I would call G2 times a 4 derivative thing. Okay. And the idea of this expansion, a priori, is straightforward. The idea is you enumerate all polynomial in phi and derivative to write down your action. But you have to mod out by integration by part, because you can always write the same thing in many different ways. Mod out by total derivative. But you can also mod out by equation of motion of the lower order. And the way it happens, roughly speaking, is that if you make a field transformation, phi, for example, phi goes to phi plus epsilon phi square. If you do field transformation like this, you're not changing the theory at all. Phi is just a dummy variable in the path integral. You're not changing the physics at all. But you will reshuffle this term in a complicated way. And in particular, the 0th order term, A will source some cubic term, and so on. So we can change the coefficient of things by adding equation of motion of the lower order theory. And in particular, as one of the exercise 4 that I've added, you could ask, well, can I write, for example, a term that's d phi squared times phi? And the claim is you to actually remove like this field of definition. So there's no physics in such a term. It is not, this G prime will be an independent parameter in your effective theory. You can absorb it in all the other ones. The other approach, which I find more straightforward, because you don't have to play this game of modding out, is to simply list on-shell amplitudes. So you can enumerate. So these two approaches are equivalent, but one is easier in practice, I find. Enumerate on-shell amplitude that are polynomial in p's. And each polynomial is going to give you an ambiguity. It's like polynomial in derivative. Polynomial in p. And because it's on-shell, you will automatically mod out by equation of motion. Okay. And because the momenta had up to 0, you also automatically mod out by total derivative. It's very effective. So if you do this, then at low energy, one of the things you can write down for one thing you have to parameterize is a 3-point amplitude. But as we said, the 3-point amplitude doesn't depend on any scale, because all the p squares are set, all the dot products of p's are set. So this is just a constant. And this is one way of understanding why you don't have to bother write derivative with a 3-point function. It's just a constant. There's no other information in the on-shell 3-point vertex. Then you ask, what are contact interactions I can write at 4 points? Let me actually write down the full 4-point function. So the 2 to 2 4-point function, once you said that this g is there, you can write exchange diagram. So you have something like this, 1 over m phi square minus s plus 1 over m phi square minus t plus 1 over m phi square minus u. This is just this diagram. Right? Once you said that this vertex exists, you're forced to have these guys. And then all the other things you can have, they will correspond to contact interactions between 4 points. So you can write the next thing will be a lambda phi. And now we're supposed to enumerate polynomials. But the polynomials also have to be symmetrical, because we're scattering 4 identical particles. So the first thing you might try to write down would be something I would call G1, say multiplying P1.P2. You could try to write that down. So that's an interaction between 1, 2, 3, 4. It involves the momentum of this particle dotted with the momentum of this particle. But this is not symmetrical. So you need to add permutations. And when you add permutations, P1.P2 is basically S plus a constant related to M squared. So this whole thing is actually proportional to S plus T plus U plus a constant. And this whole thing is actually just a constant. So in fact, this thing you can absorb into lambda. There's no physics. There's actually no two-derivative term you can write down. No term, roughly speaking, with two derivative and 4 phi's. Okay. If you wrote such a term, let me repeat, if you wrote such a term, you would compute its prediction, and you'd find its predictions are exactly the same as shifting lambda by a constant. So Bayer will not write it. The first thing you can actually write down, which is symmetrical, is G2. Now I put a Mandelstam square. It's not going to cancel. I symmetrize it. Great. So that's the first thing you can write down. And that is this G2 guy out there. That's 4 derivative. At the next order, you could write S cube plus T cube plus U cube, which turns out to be the same as STU. S cube plus T cube plus U cube. And you can prove this using that U is minus S minus T minus a constant, well, minus 4m phi square, plus 4m I square. So this is basically up to things that are proportional to the mass, which you can absorb in other couplings. You just have to write this guy at cubic order. So you see it's rather straightforward to enumerate symmetrical polynomials in Mandelstam invariants. And you have to mod out by this relation between ST and U. Okay. And then you're done. And it's an interesting exercise to classify the symmetrical polynomials you get at 4 points. And mathematicians have a big theory of symmetrical polynomials. And one interesting theorem here is that if I call this polynomial, this quadratic polynomial A and this quadratic polynomial B, it turns out that the most general symmetrical polynomial is a polynomial in A and B. So the next thing you can write down will be G4 A squared. And here I'm using a, now you can start to understand my labeling scheme. Gk as units of 1 over m to the 2k. So it's the thing with k powers of Mandelstam invariant. At the next order, so you have to enumerate polynomials in A and B. So next order, you have a G5. You can have A times B. So there's 2 times 3. That's degree 5 in Mandelstams. At the next order, you can have G6 A cube. Actually, there's a G6 prime times B square. And you can keep going. Okay? So that's a parameterization of the effective theory. Most general effective theory of a single scalar. And the question is, what can we say about this list of coefficients? Yeah.
So if I want to use A, if I want to use A as ST plus TU plus N plus SU,
that's a great question. Yeah, the question is, how about ST plus TS plus TU? This is also a symmetrical polynomial. Yeah. It looks good. It turns out to be, I think, A over 2.
Yeah.
You could use that, and it would change what I say by some factors of 2. Yeah. You could use that as your basis if you wanted. Yeah. Up to masses, it's equal. Does that answer your question?
Yes. So you could like the C-level diagram to the brief. Explain more about loops setup.
Thank you. Plus O loops. Okay? So the idea is we're going to first get bounds in the tree-level theory, and then try to correct them. That's the spirit. Okay. But it's kind of as a proof of principle. If you can't get anything interesting at tree level, like why bother with groups? Okay. We start with that. So our tool will be the dispersion relations we talked about last time. So I want to explain why dispersion relation help you in this problem. Let me take this one here. Okay. So dispersion relations. So we're going to use the complex plane at fixed t. And from now, we'll set m phi to 0. Turns out the limit is smooth, so it doesn't matter. Okay, it's not very important here. Okay. So we want to study the S-plane at fixed t. And as you heard in Sasha's talk, lectures, there are branch cuts on the real axis. And in the massless case, they go all the way to 0. And actually, they kind of overlap. If t is less than 0, they sort of overlap like this. And the thing we will use is analyticity in the upper half plane. The full upper half plane has the scattering amplitude here, with the usual plus I epsilon above the cut. There's a complex conjugate amplitude below the cut. And on the left, it's the other way around. You have m star and m. Yeah?
If we're only considering polynomials in SQ, how are we getting branch cuts?
Excellent question. How are we getting branch cut? This is the low energy amplitude. So the low, you're supposed to, oh, sorry, thank you. Here I'm doing a general case. Thank you. Sorry, yeah. In general, you have these branch cuts which go here. In the EFT setup we're considering, the branch cut at low energy will disappear and they will start at m. Okay, yeah. We'll get there in a second. Yeah. Okay. Yeah. Question?
Does the I epsilon give you a gap between the cuts?
That's a great question. The question is, is there a gap here that you can pass through? To answer to this, A, maybe. B, not needed. You should think about so this is perhaps not the way you're thinking about crossing. So in general, like here you have an amplitude for ij, kl. And this statement of crossing is that you get here m j bar goes to k l bar. Okay? So this is a statement of crossing which take an amplitude to a complex conjugate amplitude. And this statement of crossing is the one we like in this, in this approach because it's the one that uses analyticity in the upper half plane most directly. And therefore, it's the statement that's related directly to causality. Okay? So in textbooks, sometimes you do see people trying to pass through here, which is easier if you have a gap. But that's not the primary statement of crossing. This is the right way to think about crossing. Okay?
Could you explain a bit more what it means that MIJKL is above that cut?
Yeah, so this is because the standard prescription is supposed to put plus I epsilon to the Mann-Stam invariant. And for T, normally for space-like invariants, you don't have to say anything. You can take as real, but S needs to be above its cut. Okay. Good. So we're going to assume analyticity in the upper half plane. And question? Yes. Yeah, the amplitude in general is a complex object because it has, if you compute the amplitude in practice, say for example, there was Sasha gave some examples, but typically there will be something like, there will be some function like log of, 4m squared minus s. There will be things like that in that function, and be like some kind of minus I epsilon you have to put in it. So it matters whether you're above or below the cut. And so above the amplitude, this is a standard sheet, and we have a plus I epsilon. But when you go on the other side of the sheet, you have the complex conjugate of the thing.
So when Sasha gave the talk, he had this cut that's like just one, and then like go to infinity.
Yeah. So in the massless case, in general, if you do have low energy loops, the cut will start at 0. And this cut here will start at u equals 0, which is s equals minus t, which is positive. So the cut kind of overlap. You're asking why they overlap here? Yeah.
Thank you.
So that's the general situation on gap theory. Yeah.
Can you always claim that switching the sign of the I epsilon in S is equivalent to conjugating the amplitude when there's branch cuts across the board?
It's a great question. So the question, if I understand, is that one way to argue that this is M star normally is to use that there's a region in the middle where it's real, and then complex analysis ensures that it's complex conjugate below. However, it turns out that there's a way you can directly argue that it's a complex conjugate, because you can write down an analog of LSZ reduction formula that tells you directly this guy, and then you'll see that it's the complex conjugate of the correlation function. So you can write a LSZ reduction formula for generalized LSZ reduction formula for all these guys. So that we describe in a paper with Sebastian Misera and.
Can you do that for arbitrary points?
Well, the representation will converge. This LSZ sort of thing will converge close to the real axis, close to the physical region.
No, I mean arbitrary number of particles.
Oh yeah. The reduction formulas are general. Yeah. In general, you can get even out of time order correlators and funny things. Yeah, but that's a different story. So. A question I was hoping to get, and probably many of you have secretly, is, okay, physics is on the real axis. How can we be so confident that there's no dragons here? and this is where this discussion of Fourier transform last time is important. So suppose there were some branch cut here. Let's see what that would mean. Okay? So the physical picture we described last time is that we scattering some particle of energy E against some other particle of energy omega, and then when you compute this commutator, we ask that the commutator vanishes for t less than 0. That would be causality. And somehow this upper half plane thing is supposed to be the Fourier transform of the commutator. Just believe me. Okay? So the point is that large time, so this is time, not minus time t. Let me call it capital T maybe. Okay. The point is that when you do the Fourier transform, real time is controlled by complex frequencies, because you're supposed to deform the contour to make the integral as small as possible. So real time probes that part of the complex plane. If you have a cut here, what that will mean is that you have a commutator that is non-zero space-like, proportional to how far you are from the real axis will tell you how fast you decay. It will be something like x of minus absolute value of this t times s times the imaginary part of this s star, this cut, divided by this energy for t less than 0. Okay? So if you have a little bit of a causality that decays like this, you'll have a little bit of a branch cut far up there. Okay? We'll assume that there's no such thing. But in practice, if it's far enough, it's not going to matter for what I'm going to say today. Okay? If such things are far enough. Okay? So this is why we control things. Complex frequencies is related to real time.
Another question with the overlapping branch cuts.
Yes.
Here there are branch points at 0
Ah.
S equals minus t2 plus to the right.
Yeah, I think to answer this, you really have to look at models where we can calculate this. I think this is a more natural choice. Yeah. Yeah. But it's a good question. Okay. So.
Could you reiterate why you said that a little bit of a causality was okay?
A little bit of a causality thing. The question is, why is it okay? Well, it's not okay, but a little bit of a causality would change the bounds I'm going to describe by a little amount.
Oh, okay.
There's kind of a continuity there. So it's not that's an important. Let me repeat. Causality and analyticity is not an all of not or nothing statement. You violate a little bit and you change the bounds a little bit. But we're going to assume that we don't violate it at all. Yeah.
Just to be clear, is the point that this is up on the complex plane, so you imagine you took one of the operators in the scattering element and developed it in Euclidean time, so it changed the time order, and that's why it's a commutator?
Yeah, the question is, roughly speaking, why does this upper half plane thing map to a commutator? I'm afraid I can't explain it quickly. We can discuss after. I'm hoping Sebastian will also talk more about this, but let's see. Okay. The other thing that we need to know is some boundedness property. And what we will need is what I would call the Frossard lemma. So we need to know how fast this thing decays in the complex plane and analog of unitarity. And the statement is, suppose you take a normalizable wave packet of two guys. So the integral d p perp, psi of pi p perp, some wave function, times something that has some energy, and p perp, and energy 2 minus p perp. Okay, so similar wave function as appears in the homework problem 1, I believe. So imagine that's normalizable. Okay. The lemma is very simple. Is that if you take the expectation value of the scattering amplitude in a normalizable state, remember that the scattering amplitude is basically 1 minus s over I, and s is unitary, so it's bounded. Okay, and absolute value. Okay. So anyways, this. So this is lemma we use as an analog of unitarity. And importantly, because of the relativistic normalization of state, this is s times a constant. Okay, because of the way that the states are the relativistic normalization. Okay, so matrix element of scattering amplitude don't grow faster than s. Okay, this means. So the Frossard lemma, as we use it, is that this thing, let me just call it m sub phi, divided by s squared, go to 0 at s goes to infinity. Okay, yeah.
Where's the S?
The s comes because if you take p prime, that's 2e times the delta function of p minus p prime. So the standard relativistic normalization give you a factor of energy. And then you multiply this for the two particles, you get s at large s. So I call it the Frossard lemma because it's deceptively similar to the Frossard bound. Frossard-Martin bound says that m of s comma t over s squared go to 0. Okay? The Frossard-Martin bound is hard to prove. And it needs a mass gap. essentially because you have to bound the Fourier transform over a plane wave. And you have to bound interactions at large impact parameters. And that's hard. But OK, Martin did it. But the result only holds when you have a gap. And in fact, there was a nice paper by Sasha Zhiboydov and Killian Herring where they explain that in gravity it does not always hold. So we cannot assume that. The Froissart lemma is a very easy thing. I just use that S is a unitary operator, and matrix elements can't be big. OK, it's a very easy result. And it's all we're going to need. Yeah.
Is this just for scalars?
No.
What about spin J growing like S to the J?
Yeah. So this J. So the question is, how is it not violated by exchange of a particle of spin J? So where this goes like S to J. And the answer is that if you just have exchange of a particle of spin J, it violates that. However, this exchange of spin J particle only holds in some energy range. And then asymptotically, it has to flatten. So this is why the exchange of particle of spin J greater than 1 requires some non-trivial UV completion. J equal 1 is just marginal. Yeah. OK. And what this statement grants us is convergence of twice subtracted dispersion relation. Dispersion relation. And this is in any theory. But after smearing. Okay. After you integrate against some normalizable wave packet, you're guaranteed that it will work. This would actually this idea of using normalizable wave packets is actually quite natural in the context of effective stereo constraint. The idea is we're trying to probe physics at the scale m. So we're going to try to aim the particle within 1/m of each other. That's what we'd use this wave function for. OK. Let me go there. OK. Yeah, I think I will not write the dispersion relation. Let me skip a bit to. So one thing we can do, you can write down dispersion relation like Sasha wrote. And then at low energy, you can try to compare it with this Hansat. And what you find is that basically it works order by order in S. You can do this matching order in S. And the somehow more efficient way to do this is so-called dispersive sum rule, where you draw the following contour in the S plane, and you integrate over this contour and this contour. So C is the union of these contours. And this scale here is m square. And this point here would be u equal m square. So S equal minus m square minus something. And now we'll do it just in the EFT. So there's a branch cut here. And basically, we say that 0 is integral to ds over S to the k plus 1 along this contour of m S t. And technically, to be completely rigorous, you should imagine you're integrating this over this little wave function, but we'll postpone that to the end. So this is just saying that there's no singularity in this contour, so it's 0. And this contour gives us two things. It has two pieces. Yeah. Yeah.
Is that I'm using wave pockets? Is that the only difference?
That's all.
Okay.
That's all. Yeah. So it's the only situation in your life where wave packets will save you trouble. Yeah. So this I would call low energy. So I'd assume that basically this arc, you imagine this is the largest arc you could trust your low energy in. And maybe you want it to make it slightly below your cutoff. We're just going to ignore that. And then here you have mi. Okay. And so when you evaluate this contour integral on the two sides, so at low energy, and this converges for k bigger than 2. So I'm just going to write down what you get so we can get to the point of how we use it. So at low energy, the k equal to 2k's, you extract, roughly speaking, the quotient of s squared in this expansion. And that would go away. That would go away. That would be picked up. That would be picked up. So we get something like at low energy, you're doing a contour integral of this m low, and you get g2 plus g3 times t plus g4 t squared plus g5 t cube plus the dot. And at high energy, so this arc here gives 0, and you just have to include the real axis. And I've arranged the contours that what I get here is the imaginary part of the amplitude on the real axis. And for the imaginary part of the amplitude, I'm going to use I don't know what it is. It is high energy. I have no idea what is there. I'm going to use the partial wave decomposition. This is equal to an integral over s prime from m squared to infinity of sum over all spins, some coefficient Cj of s square, times some Legendre polynomial of 1 plus 2t over s prime, this s prime. Sorry. And now there's some denominator. And actually, there's a little thing I have to say here, is that you have a S channel cut and you have a U channel cut, and you're supposed to add them. But they are, because of symmetry, they are the same here, so you can combine them. And after you combine them, you get something like ds prime square s prime plus t square. And there's a numerator here that's 2s prime plus t, I believe. The details don't matter so much, but the point is that this goes like ds prime over s cube. Okay? So we get some integral like this. So you see, now we're starting to get where we wanted. You see there's some relation between UV and the IR that we obtained from the dispersion relation. Okay, all of the integral here is over the heavy states above the cutoff.
The argument in the Legendre should be 2t divided by s prime minus m phi squared.
Yes, and thank you, and I put it to 0 here. Thanks.
So yeah, you've probably said it, but the g term, you just subtracted the simple polar on the origin.
You don't have to subtract anything. So when you calculate this residue of integral ds prime over s prime cube, anything that does not grow will be killed. So lambda does not contribute, and g squared does not contribute. And you can keep going. You can do other things equal 4 dot dot dot. And yeah. So what does that mean? So notice that the main point is that the unknowns, which are these coefficients, Cj of s prime square, we're completely agnostic about what the UV physics can be. But by unitarity, these unknowns, what do they represent? They represent the probability that you create some heavy particle of state of spin J and S prime. So the unknown are positive. Notice that this is not saying that the right-hand side is positive, but somehow the unknowns in this formula are positive. The legend polynomials are oscillatory functions, but they multiply positive unknowns. And we're going to try to extract mileage from the fact that we know the sign of other unknowns. That is the game. Okay. Yeah. For those who are familiar with the conformal bootstrap, it's also a very similar game we play there. We use that OP coefficients. We don't know what they are, but they're positive. And something else which I would like to say is that because of crossing between S and U channel here, you don't actually have any information in the sum rule with 3 subtraction, the odd number subtractions. Only the even ones matter. S, U symmetry. So only info in K equal even sum rules. Okay. Okay. How do we use that? Well, the very annoying thing with this relation is that there's an infinite number of unknowns in it. So we can give up and go home. The simplest thing you can do, and I'm going to preface it with a big warning sign. Simplest thing you can do is, well, let's Taylor expand around t equals 0. Okay? And this is what we did in Vincent Van Doorn and myself a couple of years ago, and we got some kind of proof of concept results from doing that. However, you should be aware that this is illegal. Yeah. And how should I say it? Yeah. So this doesn't exist. Or more precisely, well, I'll come back later to why it doesn't exist. Let me tell you why it's useful to pretend it exists first. Okay? So why is it useful to pretend it exists? Well, if you take this thing goes to 0, then this whole thing simplifies, right? You get the sum rule for G2, and then we're going to write this sum and integral as an average. And the legend polynomial at t equals 0 is just 1. And then there's some denominator. We get 1 over s prime squared, something like this. Okay? So we can just like write each of these effectivity coefficients in terms of some sum rules over every states. Okay? This is sum over j and integral over m prime greater than m, sorry, s prime greater than m square of cj square dot. Okay? That's what this average means. And then you can, yeah.
When you do the integral from the low angle part, it seems you take the residues of this
Yes.
S, right? So why
Yeah.
you have so many times?
Yeah, because I fixed t. So this is the S plane at fixed t. So something that goes like s squared times t will be picked up. Yeah.
Follow-up question. Why are you allowed to fix t? You are eventually going to integrate over a wave package.
Yeah, so this is partly why this is illegal. Yeah, no, but the wave packet is a superposition of fixed t things, where t is a finite range.
Okay.
Yeah. So let me write a few more of those. We can write something with G3, and then this one will have, you have to take a derivative around t equals 0. So for the legend polynomial, you will get some number here minus j plus 1 times something. Okay? And you see the units work out. So G2 is supposed to have unit mass dimension of 1 over mass 4, and that's what I'm making manifest here. And then there's G4, and then you get this thing, 4. An interesting thing is that you can look at the coefficient of S squared T squared and S4, and they have to be related by crossing. So that is also the key to this thing. You get some rule that it's possible to write 0. There has to be some averages which give you 0. So here, j plus 1, and then some number. Let's call it a, let's call it 1 minus some number, j plus 1. So there are some averages which have to give 0. So that says basically that IR crossing constrains the unknowns, heavy unknown. Which are basically heavy, light couplings, Cj squared. So these couplings are not arbitrary, sorry, heavy, light couplings. So these couplings are constrained by crossing. So we have a bunch of unknowns, but they're not completely unknown.
So in the right-hand side of these equations, all the Cj appear, right?
Exactly. All of the unknowns appear. So you have an infinite sum. It's kind of a two-dimensional space, this spin, this energy, and you have all these weighted averages over these unknowns. But somehow this is going to prevent, so you see the fact that this is going to 0 is somehow going to prevent you from having too many high spin stuff, and it's give you various constraint that low spins have to balance against large spins, and there's a lot of interesting constraints that come out of that. And the other part of the exercise, and this is relatively, you really have to do it by hand, but yourself, but it's relatively straightforward that it comes out, is that from that you get some interesting bounds. Some of the bounds are really easy. Because S prime is bigger than M squared in this bound. Actually, there's a 1/2 here, I think. But it's very easy to show, for example, that G4 has to be less than G2 over M4, maybe with a half. Okay? So you get inequalities from the fact that it's positive sum. So you get a bunch of inequalities, and that way you can start to, and also maybe a more basic one I should have said, is that G2 has to be positive. Okay. If you have any UV physics, this guy will be positive. And if you start to manipulate these inequalities, you get basically exclusion plots on these G. So let me plot to visualize what we get. So you have to make ratios. So this approach doesn't tell you anything about what G2 can be, but it compares G4 to G2, G3 to G2, and so on. So if I make here on the axis, I put G3 compared to G2 in units of the cutoff versus G4 over G2 with the M4 to make it dimensionless. G4 has to be positive. It's bounded above by half. And then turns out you get an allowed region that looks kind of like this. And yeah. So the claim is that any effective theory that is causal must have this G4 and G3 lie in this shape. Outside of it, you will violate one of the assumptions. And I can say a bit more about the, let me say one more thing about this graph. So actually there's a little shape here that's a bit odd. Whenever you have there's also something that is resonates with Sasha's lecture. Whenever you look at the space of theories and you try to extremize some observable, you maximize, minimize something, you'll end up on some unique special theory. So we can ask, what is the theory that lives at this cusp? It turns out it's not a very exciting theory. This M1 ST is just what you get if you integrate out a heavy scalar. So it's 1 over m squared minus s plus 1 over m squared minus t plus 1 over m squared minus up to an overall normalization because we're just bounding ratios of coefficients. So if you expand that at low energy, you'll get a constant, you'll get a term with s squared plus t squared plus u squared, that gives you G2. You get the next term that gives you G3. So you can match this to the FT, and you land on this point. Okay? Maybe I can say it. So this is like 3 over m squared plus s squared plus t squared plus u squared over m6 plus dot, dot, dot. Okay, so you just Taylor expand this at low energy, and you match it to read off G2. Okay? And then you keep going to get G3 and G4. So, yeah.
But in this case, the calculator just wrote down as no cut. So like.
Yeah, it has no cut. So the whole spectral density was a pure pole here. Yeah. One thing you can do, thanks for the question. The question is, okay, why is no cut? Well, actually, now that I have this amplitude, one thing I could have is I could take integral of, I don't know, this M1 ST, which is a function of this mass, and I could integrate it over some spectrum of mass. And it turns out that doing this operation will span this line. So if you change it, if you superpose this theory with, well, if you take one theory with different mass, you will be on this line. And if you take theory with different mass, so if you superpose a theory with this mass and this theory with this mass, you will end up on this line. And the convex all that relates down. So you can take superposition of theories and you start filling the space. The other theory, M2, is also, we're able to identify it. M2 is weird. M2 is 1 over m squared minus s, m squared minus t, m squared minus u, minus a multiple of f1. The small, you can try to subtract, and the largest thing you can subtract, still compatible with unitarity. That gives you this guy. I should not call this a theory. Nobody knows if this is a sensible theory. But it has a well-defined amplitude. It satisfies all the axioms of the positivity of partial waves and so on that an amplitude needs to satisfy. So the claim is that, and actually this theory, now you start taking combination of this theory with different masses. You fill the space, and you take linear combination, you fill the space. So basically, almost all of the space of causal EFTs is spanned by linear combinations of these two guys. So if you want to have an idea of the space, these two guys give you an idea. Almost full space spanned by linear superposition of M1 and M2 with different masses. Okay, so that's a characterization of the space. So that gives you a flavor of what you can show.
So a question over there.
So I know that we're ignoring loops for the moment. Let's
Yes.
say that we first started loop effects and we started with a theory that's close to the boundary.
Yeah.
Could you put causal constraints on RG flow to say like you can't flow outside of this boundary or so that like constraints?
Yeah, it's a good. Yeah, the question is whether there are interesting constraints on RG flow and how it fits. Yeah, the answer I'm not quite sure. I'm not quite sure. Yeah, the RG is a bit complicated. Is a bit tricky because you will have term that goes like lambda times the things you added, but you also get nonlinear term like G2 squared can mix with G4. So there's a quite rich RG. I haven't studied it, so I can't say, but it could be interesting. So let me step back and make a few comments. Great.
Could you clarify where in this we used causality? Because it seems
Yes.
like we used the Crossart lemma in this argument, and that we didn't derive using that property of wave packet. So
Yeah, we use causality in a very fundamental way here, because we use analyticity in our path plane to write down the Kramers-Kronig dispersion relation. So this looks close enough to Kramers-Kronig that I call this causality. Thanks. Yeah.
Why did that? It seems this is a supergravity or some stuff.
Yeah, that's true. That's a supergravity. The comment is that this looks like a supergravity amplitude after you strip off some SUSY delta function. Yeah. The funny thing is here, there's a scalar, so there's nothing, no numerator to strip off. So it's a strange thing. Yeah.
Is there anything interesting about the things that saturate the down but aren't in the corner?
Yeah, these guys. Yeah, there's actually a nice story by, I think it's still under progress, but they have they can nail, they have a numerical procedure, Elvang, Henriette Elvang, and I forget the name of our collaborators. They have a nice way of nailing this theory numerically, but we still don't have an analytic understanding of this little strip.
It's not like it's some family of theories with a kind of constant tunable parameter or something.
Yeah, it is. Yeah, exactly. There is a family of theory with a constant. At least here there's a tunable parameter, but we don't have an analytic form of this theory. So I want to step back, and one of the messages I would like to make is that notice that lambda, the phi-4 coupling, did not appear here. And that's because this contour integral only picks the things that grow with energy. So the way we say this is that lambda is not dispersive. It's not a dispersive coupling. And yeah.
Sorry,
Yeah. Sure.
how did you check? Did you check the? Oh, sorry. Can we believe this diagram if you have consider higher and higher correction?
Thanks.
Maybe there's some additional cut or something.
Yeah. I can say a bit more about the way this is obtained. So if you use only these 4 equations, you'll get some shape, which is a bit bigger than this one. Yeah, but the game is that you have many such constraints. So there's a game of optimizing all these constraints to prove the optimal bound. And this is what we believe is a converged result, which you get there after, I mean, you try with many, but after like 5, 6 constraints, you get pretty close. Yeah. So one question I often get asked, and I want you to know the answer, is how about standard model couplings? So there's a big program at LHC to constrain standard model effective theory for physics beyond the standard model. And the result of my unpublished, so we can go through all the 2000-something standard model EFT operators, and well, most of them are just like 4 fermions with different flavors. But you can go through them, and it seems that none of them are dispersive. So that's very sad. So it means that if you draw a Venn diagram of the couplings we can bound with this technique, with 3-level technique, dispersion relation, and couplings that people care about, they may overlap a little bit in some minority opinion. Some dimension 8 operator that maybe some people are interested in, but that is the truth that I need to disclose to you. Okay?
When you say you get these constraints from Taylor expanding?
Exactly, which is not supposed to do. You're not supposed to do, but you get these constraints. So maybe that's a natural place to ask, how do you do better than that? Because actually we can get the same constraints without doing this dirty step. So thank you a lot for this question. So the more modern approach to this is that you're not supposed to fix T. There's a very clever other parameterization that instead of fix T, you can use something that looks like fix T at large energy, but is a bit more clever otherwise. It's called a crossing symmetric dispersion relation. And the idea is to fix 1 over p squared equal to minus 1 over s plus minus 1 over t plus minus 1 over u. You fix this combination. And as always, you have s plus t plus u equal to 4 and 5 squared. So you have basically one free variable. And I won't go through the details. You can get a bit of a flavor of how it works from the, well, you can get the full flavor from the reference I gave in the homework problem 4. But I can give you a formula for what you get from this. So if you play the same game of having low energy equal high energy, this contour integral, and this extra variable, what you get is very nice. What you get is something that automatically terminates. You get g2 plus g3p squared is equal to some heavy average exactly like this. But now the thing that's different is that the argument of the Lejeune polynomial is a weird thing that is s prime minus 3p squared over s prime plus p squared. And this crossing symmetric parameterization, somehow it's using all 3 channels at the same time. It's very clever. And so instead of somehow using crossing symmetry by hand and this Taylor expansion order by order, this manages to use a crossing symmetry in a global way that's much more clever. And you get this, and there's some kernel here. I think it's s prime cube 2s prime plus 3p squared, something like this. There's some kernel you can find in the work. And you have some things like this. And this, the important thing is that this terminates. You only have a finite number of coupling. So you do the twice subtracted dispersion relation version of this, you get 2 couplings. You do the next version of this, you get the 3 next couplings. You get a finite list of couplings at each order. It's very powerful.
Is the final result the same?
Sorry?
The final result of the same.
Yeah, so at the end of the day, now you can do the rigorous thing. You can integrate this against dp times some wave function of p to get rigorous bounds. And what you find when you do this exercise is that, so you can make an ansatz for psi, which is like polynomials of higher and higher degree. And then you look at the thing that come out of the computer, and you see that the computer would get more and more clever at computing using wave function that compute derivatives around 0. So you get the exact same plot. So you work much harder. But you get this exact same plot. However, now it's actually a much better starting point. Now this is more stable against loops. The forward limit is not stable against loops. You get this is stable, and also works when you have graviton exchange. Works with graviton pole, which as a term, can add it here. It would just add the g Newton over p squared here. But if you integrate like in the wave packet that's suitable, it doesn't not a problem. So it automatically handles this nice business. So I can quote. I think I quoted in the paper that did this extension by the loops by. We're not name all the others, so I would just name the conclusion. You can find it. In true Confucian fashion, the effects may be small, but the changes needed to introduce them are significant. So yeah.
Even if it's stable against loops, then there's no chance of that diagram overlapping.
Yeah, they overlap a little bit in dimension 8 operators that some people might be convinced to care about. Someone.
I was trying because the diagram that left
Yeah.
circle was tree level.
Yeah, but loops are not going to help you. No, loops are not going to help you. So the loops effects end up being finite corrections to this story. Well, actually 0 correction to this plot. Okay, so I'm almost done. Yeah, and when you do this for gravity, now it's stable with the graviton pole. And now you can actually start analyzing gravitational theories and graviton scattering with this. You can do much more than the scalar theory. And for graviton scattering, now these estimates we had last time become actual bounds. So I will just quote some bound. So from graviton scattering, you get bound. So last time we talked about the coefficient of, say, something like Riemann square, Gauss-Bonnet in our dimensions. And now we get actual bound that, maybe I can sketch why it's possible. I think I have time to draw one more equation. So for graviton scattering, now this sum rule includes the graviton pole. So we can write a sum rule for G Newton. There'll be some integral or some average of something, and Pj is some Lagrange polynomial divided by S prime some power squared. Okay. Then you write a sum rule for lambda. Yeah, this is integral over some wave packet. And then you try to get a sum rule for, say, the coefficient of lambda Riemann square. Actually, you get this coefficient square. Now you try to get some other wave function, and then it's S prime 4. Remember, gravity needs to be attractive. And actually, you can make this manifest here. You can find a wave function psi such that this is positive, which is a sum of positive terms. This is only a sum of positive terms. So we have a sum rule which demonstrates that gravity is positive. Which, okay, again, why do you care? Well, you care because as soon as you have a sum rule which tells you that gravity is positive, you can write down any sum rule for anything else, and it's going to be dominated by the sum rule for G Newton. So you automatically, by comparing this sum rule, you automatically learn that this lambda, maybe I should put a G Newton here on the left, this lambda Riemann square is less than some power of the cutoff. And you can actually arrange this sum rule so that it only cares about particles with spin 4 and higher, exotic heavy states. So you learn that, and this would be, maybe I'll put it like this, m square, j greater than 4. So what you learn from this type of arguments is that in order to, whenever you modify gravity, you really need a new particle that has spin 4 or higher at a very specific scale here. You have precise number here. So one of the things, for example, that we managed to show using this is that in D equal 5, where you take the flat space limit of ADS5 cross S5, the graviton amplitude maps to center charge of the theory, and we get an interesting bounds on the center charge of n equals 4 spring angles is less than 23 over the higher spin gap to the square. So we get this type. So we get rigorous numerical results that bound corrections to higher derivative corrections to gravity. Let me finish. Yeah, so I have some general conclusion here. So I think the main message of this lecture was that spin is a powerful tool to constrain theories. spinning particles are more constrained than scalar theories, although scalar theories are already a little bit constrained. One particular result we obtain about gravity is that if you start adding higher derivative correction like this to gravity, there's a length scale associated with these things. And this length scale has to coincide with the Compton wavelength of a spin 4 particle. So as soon as this term competes, as soon as these two terms compete with each other, you should no longer use the effective theory. You should go to the more fundamental description where you actually have the spin 4 particle floating around. And then, okay, a bunch of other directions. So I omitted to tell you, but in 4 dimension, all of these bounds have a log, infrared log divergence. We can talk more about this, but it would be nice to improve that. Other thing that completely does not fit the framework I described is the so-called, I only look at the finite dimensional representation of the Wigner group for massless particles, but they are the so-called continuous spin. There's interesting progress by Tohu and Schuster. Maybe we can actually say something interesting about whether these things can exist or not in nature. But these things were not covered by what I talk about. I think this idea, I emphasize gravity to make it self-contained, but a lot of the ideas can probably be used for correlation functions in QCD or other theories that you might be interested in. So maybe there are things that we can say not just about pions in QCD, but about local operators and which satisfy similar mathematics. So that's for the future. Yeah. So that's all.
I think we're a couple minutes over, so we'll hold questions till the coffee break as usual. But this was Simon's last lecture, so let's thank him again.